Okay, now we're gonna code the conv layer of the liquid foundational model. So let's quickly have a look at how it looks and what its architecture looks like. So as you can see, we have the input, and input is is of this shape BLH, which is technically byte size, the sequence length, and the hidden size. So what we do, we put it into a linear layer, and we just we can say, replicate this H1, the hidden size, into 3. And the reason for that is because we want to feed each one into one of these gates and one of these pipelines. So one of them, one part, we can say 1 BLH goes to gate B, 1 BLH goes to this side value X proj, and one of them goes to gate C. So technically, after this linear layer, the way that the shape would be BL3H. So yeah, and after that we have gate B, gate C, and if you remember in the introduction, I said these gates are very important because, as we said, in the liquid foundational models, one of the big differences or innovations is that the input and the state of the neuron or network in fact is dynamic, and this because it is a differential equation, and the way that we try to mimic that is by having these gates. These gates will be learned by the input shape, input size, or whatever the input is, and they will kind of adapt themselves by the input. So they have the ability to, for example, I don't know, just copy the human brain, for example, spend more time on processing or whatever that it is. So what happens here is that, okay, we give one data source to gate B, and then what we do is right after that gate we have a multiplication to this X proj, and then we have a depth-wise convolution, one-dimensional convolution, and then on the other side we give it to gate C, and the result of that will be in fact multiplied to see in fact the result of this convolution. And after that we have dropout and a linear layer, and then we have the in fact output. But how it looks like in the code, let's see. Okay, so I can say port torch, and I can say import torch.nn as an n. I can cheat from here, which I have it in the technically autocomplete. So yeah, technically, as you can see, this is kind of the definition of how it looks, and I'm gonna remove this, however, for now, and then we can define the init function. What it will have as a in fact input is this lfm2 config, and if you remember, we had a couple of things in the config file. For example, I don't know, for the conv layer we have the kernel size of the conv, the hidden state, and so on and so forth. So yeah, let me save this, and then we have super init. Then we initialize the config, initialize the hidden size, which comes from the config file, which I guess it was, let me accept this, and I feel like it was 100, was 1000 or something like that. Yeah, 1024. And we're gonna define this input proj. And what is this input proj? It is the same as, if you remember, we had this linear layer which accepts h and replicates it 3 times. So this is technically what happens. We have the hidden size, and the output would be 3 times the hidden size, and the bias is false for now. Then we can have in fact technically, what is it, the config, the convolution part. So again, the convolution is again the hidden size, and the hidden size again comes from the config file. We have the kernel size. The kernel size, I guess, like it was, how much was that, 3? Yeah. And then the padding, and I don't know, the hidden depth wide convolution efficiency. We're gonna group them, and if you want to know more about this grouping, just feel free to have a look at it, that why this grouping happens, because it is more efficient technically in computation and so on and so forth. Just search the name and you will find out everything about this grouping of the convolution layers. And again, the bias is false for this convolution layer as well. And what else we have? We have then technically the output projection. Let me accept this as well. So we have so this one was convolution layer again, which we use it right here. And then the other one, which we need to define right now, is dropout, and then the final projection or linear layer for the output. So the output projection is simply the hidden size, and then input is the hidden size, output is the hidden size, bias is still false. The dropout is just technically a dropout with this percentage, and I believe the percentage for the dropout was 0. Again, feel free to change it to whatever you like. Where is it? It should be, I cannot find it. I'm pretty sure it was 0. Yeah, right here. Hidden dropout and attention dropout, they are 0 right now. And then what we're going to do is we technically define the forward pass for the conv layer. I'm not gonna write these descriptions or docs strings. What the input, so we have the input as x here. What the input is going to look like here is, so the input shape is going to be batch size. Let me say batch, yeah, the batch size, sequence length, and the hidden size. So this is how technically our input looks like. And what are we going to do is, let me check if this is correct. Yeah, we have the input, it looks like it is correct. So we give the input x into input projection. Again, in the graph it will replicate it 3 times. It will be replicated 3 times as we defined it here, right in this line. Then what we can do is, so now the shape is going to be, the previous shape before any manipulation was b, c, x, or let's say l, h, whatever, batch size, sequence length, and the hidden size. So after this projection it would be batch size, sequence length 3 times hidden dimension or state. And then what we need to do is we need to chunk it and in fact kind of disentangle that, and each of those tensors would be BLH because we want to give each of them to each of these in fact paths. And now we have 3 of them. One of them is going to be the, what is it, B gate, C gate, and proj X. So the B one is going to be so what we understand is going to be projected, it's going to be, what is it, multiplied by projects right here as we saw, and then it then we will apply the convolution to that. So we can call this x gated or the gate B, something like that. Then we will have this shape of it, and what technically we have next is going to be, yeah, we're gonna have the convolutional layer. We're gonna apply convolution into that, and yeah, and this transpose is technically because we want to change the order of this, what is it, H and L, the first and the second and the third position right here. and then we give it to the convolution layer, and then again we do the transpose to go back into the initial structure. And then on the other side we have the C gate again, this side. So we did gate B, multiplication, convolution. Now on the other side we have gate C, and then we need to do another multiplication and then drop out and linear layer. So here is the gate C. We multiply it by, where is it, x conv, and we have the result of them. So this line would be technically everything all the way up to here. Then the dropout, and right after dropout we have the projection, and after that technically we have the output, and yeah, so we have the result technically. So this one was for the convolution layer of the liquid foundational model, and next we're gonna go to the in fact next part.